Welcome to The Explainer. So today we're tackling something pretty massive. We're going to break down exactly what it takes to scale a website all the way from literally 0 users up to handling millions of concurrent users without the whole thing crashing down. It's an absolutely fascinating evolution of system design, and I'm super excited to walk you through it. You know that old saying, right? A journey of 1,000 miles begins with a single step? Well, building a complex system is really no different. We're not just going to skip to the end and stare at some crazy, tangled web of servers. Nope. We are starting right at step 1. We're going to build this thing up logically, piece by piece, so you know exactly why every single component is actually there. Step 1. The single server setup. This is the bedrock foundation of our entire system design journey. Okay, let's just dive right in. What we're looking at is your classic single server setup. When you're just getting off the ground, everything, your web app, your database, your cache, it all lives on one single box. So a user types in your domain name, the DNS returns an IP address, and boom, their browser or app sends requests directly to that lone web server. It's simple, it's elegant, but man, as your user base grows, you are going to hit a wall hard. And that wall is basically you running out of space and juice. So you've got 2 options here. First, you can scale vertically, meaning you just beef up that one server with way more CPU and RAM. And hey, it can work. Amazingly, back in 2013, Stack Overflow was handling over 10 million monthly visitors using just one master database. But get this, it had 24 terabytes of RAM. That is massive. But vertical scaling has a hard physical limit. Plus, it gives you exactly 0 redundancy. So for truly large-scale apps, we have to look at horizontal scaling, or scaling out. That just means adding more servers to the mix. And to scale out effectively, we move to step 2, scaling out the database by separating our tiers. So imagine for a second that your entire database is just sitting on that one single server. What happens if, say, a typhoon or an earthquake hits that exact data center? Poof, literally gone. If you've only got one database, your data is vaporized, and your site is dead in the water. We call this a single point of failure, and let me tell you, it's pretty much a system designer's worst nightmare. The ultimate fix for this nightmare scenario? Database replication. We set up what's known as a master-slave relationship. Basically, the master database handles all the data-modifying commands, your writes, updates, deletes, all that stuff. Then it actively copies that data over to multiple slave databases, and those are the ones handling all the read operations. Now, since most apps have a way higher ratio of reads to writes, having all these slave databases lets us process so many more queries in parallel. And the best part? If one database suddenly goes dark, we have instant failover protection, 0 data lost.
Okay, so our data tier is looking pretty bulletproof now, but by fixing that, we've kind of made our front end the brand new bottleneck. So let's jump to step 3, balancing the load.
Think about it. Even with our databases safe and sound, what happens if millions of users try to smash our single web server at the exact same millisecond? It hits its absolute limit. People get those agonizingly slow loading screens, or the whole thing just crashes offline. We absolutely have to eliminate this single point of failure on the web tier. Enter the load balancer. This thing is the absolute hero of system design. It elegantly distributes all that income and traffic evenly across a whole pool of web servers. The users, they just connect straight to the load balancer's public IP address, and then the load balancer quietly and securely routes them to the web servers using private IPs. If one web server starts choking or dies, no problem. The load balancer just smoothly redirects traffic right over to a healthy one. And this completely illustrates how far we've come. You can really see the system growing up here. The user hits the load balancer, it routes them to our shiny new redundant web servers, which then read from the slave databases and write to the master database. We have successfully killed our single points of failure. Huge win. But, okay, honestly, it still might be feeling a little sluggish. See, our system is super reliable now, but hitting the database over and over again, that takes time. So let's move to step 4, speeding up with caching. To take the load off our database, we bring in a read-through cache strategy. Here's how it works. When a server gets a request, it checks the cache first. Think of the cache as a lightning-fast temporary memory store. If the data's in there, awesome, it shoots it right back. If it's not, it quickly fetches it from the database, drops a copy in the cache for next time, and sends it to the user. Leveraging tools like Memcached means we can instantly grab popular data without even waking up the database. It's a total game changer. Now, for the heavy static stuff like your images, videos, JavaScript files, we use a content delivery network or a CDN. These are essentially servers scattered all over the map. Why do we care? Well, if your main server is sitting in Europe, a user over in San Francisco is going to feel that lag. A CDN totally fixes this by caching those static files locally all around the globe. So when that San Francisco user requests an image, the server right down the street delivers it. And it just hangs out in that local cache until its time to live, or TTL limit, finally expires. Just take a look at how our core web and data tiers are now totally shielded by these new speed layers. The CDN is out there intercepting the static asset requests right off the bat, while our cache is sitting snug beside the databases, keeping their workload light. Honestly, the performance jump at this stage, it's literally night and day.
But what happens when we start going truly global? That brings us to step 5, stateless architecture and scaling.
Now, what's really interesting here is the stark contrast between these two setups. Look at the stateful architecture. It's storing users' session data, stuff like your login state or profile pic, directly on the web server itself. This forces us to use these messy, sticky sessions where user A has to be glued to server 1. If server 1 crashes, boom, user A is logged out completely annoyed. But then look at the clean stateless design. We just rip all that session data out and drop it into a shared NoSQL data store. Suddenly, any web server can handle any request from anybody just by grabbing the state from that shared storage. It makes autoscaling so incredibly simple. And once those web servers are stateless and autoscaling nicely, we can start dropping entire data centers into different regions worldwide. To route everybody properly, we bring in GeoDNS. This clever service resolves IP addresses based entirely on where the user is actually sitting. So your buddy on the East Coast gets routed straight to the US East data center, and you on the West Coast, you're going to US West. Seriously, just take a second to appreciate the massive scale we've achieved here. We've got entirely replicated data centers. And the absolute best part is the failover. Let's say US West goes completely dark, just a total outage. Our GeoDNS will seamlessly route 100% of that traffic right over to US East. It's so smooth, the users won't even notice a blip. Okay, we're serving millions now, but there's one final layer of polish we've got to add. Step 6, decoupling with message queues. So to handle really heavy background tasks without tanking the main website, we decouple things using message queues. Think of a message queue as a giant memory buffer. You have a producer, like our web server, and it grabs a heavy request, like say a user uploading a massive photo that needs to be cropped and blurred. Instead of doing the work itself, it just drops a message into the queue and instantly tells the user, hey, task started. Then later on, a consumer, like a dedicated background worker, comes along, grabs the message, and does all that heavy lifting behind the scenes. Because they're fully decoupled, you can scale your web servers and your background workers totally independently. It's brilliant. Now, let's be real. At this kind of massive enterprise scale, certain tools go right from being cute nice-to-haves to absolute survival necessities. You literally cannot run a system like this blind. You need centralized error logging to catch fires instantly. You need deep metrics to track things like host-level CPU, memory, and big business metrics like daily active users. And you absolutely need automation, like continuous integration, to test and deploy your code across all these global servers without any human error creeping in. And guys, that brings us right back to our core philosophy. Scaling to millions of users, it's not magic. It's just a methodical, step-by-step journey of hunting down bottlenecks and decoupling your systems so you can keep refining them. I mean, we started this whole thing with one lonely server, and look where we ended up, a globally distributed, stateless, auto-scaling powerhouse. It's like a giant puzzle, and putting it together is incredibly rewarding. So the only question left for you is, what's going to be your first step? Thanks for hanging out with me for this explainer, and I'll catch you in the next one.